Good evening, welcome to Lecture 5 of Topic 2 of Unit 4, Ray Diagrams for Lenses. This video will be covering the main ideas of Chapter 16.7 of Book 1. Please complete this reading before class. Here are your learning intentions and success criteria for the chapter. Please pause the video and attempt to complete the KS table down the bottom right there. Okay, so we can see here the learning intention is about constructing ray diagrams for two types of lenses. And the goal of this is so that we can determine the image location and nature, so our two success criteria about construction, and then we need to be able to describe the nature or the properties of the image. So we need to know what our lenses are. If we don't know what they are, we can't construct our ray diagrams, and we need to know what properties an image will have so that we know what we're going to describe about it. In terms of skills, it's about this construction. Can you do it for a concave? Can you do it for a convex lens? They are different things. Sorry, it's a bit breathing issues. So, as we saw with refraction, when light changes from air to any medium, the light bends towards the normal. And if it goes the other way, from the medium back into air, the light bends away from the normal. So here's an image to help us see that. So we can see here, as the light comes from the air into water, we see the angle. So there's the angle of refraction there at the top. Here's the angle of refraction here at the bottom. Oh, sorry, angle of incidence, angle of refraction. We can see that as it goes from air into water, it bends in. And so the opposite would also be true. If we went coming out of water along this angle, that would be the outgoing angle. Now, when you set this up with shapes other than a rectangle, you get an interesting effect that light bends towards the thickest part of the prism. So here it is using triangular prisms. You can see as the light comes in, it bends in towards the thicker part. This is the thin part, that's the thicker part. And then as it leaves, it also bends towards the thicker part again. And that's because the normal is pointing in two different directions. So this whole idea of bending towards or away is still true. It's just that because of the fact that the normals are not parallel with each other, the normals are at different angles to each other, we end up with this interesting bending effect. So whether it's upwards, we see if the triangle is pointing up, it bends down, if the triangle is pointing down, it bends up. Now that's not that important, but it gets us to see where this is going. If you take a shape like this, a triangle, and you shape it properly, you make all the light converge, which means come towards, or diverge, which means go away from a single point. So here we have two examples, converging and diverging. So here we see all the light is coming towards, and here we see all the light is going away from this point over here. And this is called the focal point. Okay, all lenses, and these what these shapes are, they're lenses, all lenses have a focal point. Okay. Lenses come in two shapes, concave, convex. The way I remember it is that for a concave lens, light goes into the cave. So if this is like the opening of the cave, the light goes into the cave. Okay? And then convex is the other one. So let's talk about lenses first. When we look at a lens, it looks almost like a small piece of a circle. And as such, lenses are often described as having a radius of curvature. Okay. Generally, it's given the symbol R. Technically, because it's a length, it should be in meters, but as there's no required formula for lenses, any unit's fine as long as all your measurements are in the same unit. So when we're dealing with the radius of curvature and the focal length and how far away the object is, all these just have to be in the same unit. So if one thing's in meters, everything has to be in meters. If one thing's in centimeters, it all has to be in centimeters. Okay. What is really important though is you have to draw things to scale. Here's an example. So the second bit is focal length. And this is always half the radius of curvature. Okay. So if you have been told the radius of curvature, you can work out the focal length by just dividing it by 2. This formula is not given to you, but you should understand the relationship and this formula just represents that. And finally, whenever you do a lens diagram, you have something called the principal axis. Oh, there's my image. And the principal axis is just the middle line. So here is an image that sort of helps us understand radius of curvature. Here's our lens. this part of it here could be described by a circle, and so the radius of curvature is just some distance away from the lens, and then the focal point will be some distance towards it, in between the two. But here's all these things in one bit. I know this is with a mirror, but I couldn't find any fantastic images that used a lens for this instead, so just pretend instead of saying convex mirror, it says concave lens. From the distance from the center point, curvature, focal length is halfway, and the principal axis is the line right through the middle. Okay. So, lenses and focal points. For convex lenses, here's our convex lens, the rays are drawn converging to the distant focal point. So if the light is coming in from the left, generally I always do mine coming in from the left. It doesn't matter, but just convention, we just put things coming in from the left. We see that it's converging to the focal point on the right there, on the distant focal point. And you saw that in your labs when we played around with lenses. For concave lenses, it is drawn with they're diverging away from the close focal point. So here's a focal point on the same side as the light coming in. We see everything is spreading away from that point. And that's really important to keep in mind. Okay. Now, we're going to draw some ray diagrams, and there are 3 rules we need to know from this. Okay, so, line 1. Line 1 always goes parallel from the top of the object to the lens, and then through a focal point. Okay, now, I can't say which focal point because it's going to differ depending on whether it's convex or concave. When it's convex, it's going to go through the distant one. When it's concave, it's going to go through the closest one. Line 2, very easy, goes straight from the top of the object through the center of the lens and just keeps going straight. You don't need to bend it, it's just straight line. Nice, easy one. Line 2, really easy. Line 3, okay, goes through the focal point of the other side. And what I mean by that is, of the same side. So what I mean by that is, if the object is on this side of a convex lens, it's going to go through this focal point over here to the center and then parallel, while on this one, on a concave lens, because this side, okay, is coming from this focal point, it needs to be drawn towards that focal point and then parallel. Really hard to describe. We're going to have to see some examples. So line 2 really easy, and line 1 and line 3 are reverses of each other. So parallel to the lens and then to the focal point, to the focal point to the lens, then parallel. Now, you only need 2 lines to figure out where the object goes. You may need all 3 for full marks on any ray diagram questions, and I just don't know at this point because we haven't seen any, and there are no examples that I can draw off of from the syllabus. So I'd maybe keep in mind trying to keep all 3 for it. So let's have a look. This is pretty similar to what we did in class. Here is our basic setup. We've got our lens, I've got the focal point marked on each side of it, and I've also got the radius of curvature. We've got our object. Now notice the object, the base of the object, is sitting on the principal axis. That just means I don't have to do anything from this point, because if my object is sitting on the principal axis, the image will be sitting on the principal axis. If the object was not on the principal axis, I would have to do what I'm about to do twice, once for the top of the object and once for the bottom of the object, which just means twice as much work. So save yourself some hassle, draw your object sitting on the principal axis. So line 1. Hopefully you've got those written down. So if not, go back and write them down, because I'm going to talk, I've got them in front of me as I read them off. So line 1 goes parallel from the top of the object to the lens. So from the top of the object to the lens. Okay, we can see that going there from the top of our object to the lens. And then it goes through the focal point. Now, this is a convex lens. Light that comes parallel converges to the distant focal point. Okay, if I go back to that previous image, light that comes parallel converges to the distant focal point. So that means my second line, my line's going to go through there. Okay. I like to draw it fairly long, just in case you don't know where it's going to converge off the top of your head. So just draw a reasonably long. It's not like you're going to waste space or anything. Line 2 is the easy one. Straight from the top of the object through the center of the lens, so here where it crosses the principal axis, and just keeps going on straight. So we can see here that these two lines are converging over here. Well, that's good, because that means that's where our image is going to be created. So our image should be created here. And I'm going to do my third one. Remember, the third one goes through the focal point to the lens and then parallel. So the focal point's right here, so I'm going to go through the focal point to the lens. Now it'll end up down here, but that's okay. Okay? The fact that the drawing of my lens, it's not hitting the drawing, that doesn't mean anything. You could, if you just keep in mind that it's convex or concave when you draw it, you could draw your lens as just a straight line right down the middle, because the shape of the object there really doesn't mean anything. Definitely draw it using the proper shape, because they're going to be marking on that. Okay, but you don't. It's the shape doesn't mean anything. So top of the object, through the center to the lens, or at least in line with the lens, and then parallel. And we see it goes over there, and so they would all converge just a little bit past the scope of my drawing there. Maybe I should have cut that off a little bit. And so if I was to draw my image, I would draw my image over there. Now let's use a bit of language here. We can see that it's upside down. So if this is the right way up, this is gone the other way. So this is an inverted image. It's also what we call a real image. It's on the other side of the lens from our object. And in this case, it looks magnified, it looks enlarged, it's increased in size. The only way to do that is to actually measure it, though, on these sort of things. There are some equations that I'll show you at the end, but they're not within the scope, so don't stress about those. So this is a pretty common one. Now, if I take my object anywhere up to the focal point, or anywhere back past the 2f, or the radius of curvature, all the way back to infinity, it'll keep doing stuff over there somewhere, and they'll always be upside down, they'll be real, and the magnification will vary depending on how close you are to it. But we want to have something different is going to happen when we do it in between our focal point and our lens. So let's move our candle into there. We're going to follow the same rules. Line 1, nice and easy. Parallel from the top of the object to the lens, and then through the distant focal point. Okay. Line 2, from the top of the object through the center of the lens, and keep going straight. Now, if you're looking at them and go, those don't converge, that's a problem. And line 3 is going to make it even worse. Remember, line 3 through the close focal point, or in the same side focal point, excuse me, up to the lens, and then parallel. So it's going to go from here to the top and then to the lens. Okay, so it has to. It's on that same side focal point, and then it goes parallel. None of these things converge with each other. So does that mean there's no image? No, it doesn't. It just means that the image is created virtually. Okay, so now what I'm going to do is I'm going to backtrace each of these lines. So my first line, I'm going to backtrace this line that's going through the focal point. I'm going to backtrace it up here. Second line, my line that's going straight through the center, I'm going to backtrace it up this way. Now we can see they're converging over there. And third line, backtrace it parallel. We see that they all converge. And so now my image is here. So something interesting happens, or something important happens, as you go from past the focal length to in front of the focal length. We go from creating a real image over here to creating a virtual image over here. So this is called a virtual image. It is upright because it's not inverted, it's on the same side, and in this case it's magnified as well. Okay, so they're the only two things you can get for convex lenses. Either it's going to be, if it's past the focal point, it'll be a real image upside down over here. If it's in front of the focal point, it'll be a virtual image, and it'll be on the same side, and it'll be upright instead of upside down. Okay, and we'll get to summarizing this language on a later slide, so don't worry if you're trying to furiously write them down. Let's have a look at a concave lens. Now, concave lenses, doesn't matter where you do it, they will always do the same type of image. So I am just doing one on this. Same thing, I've got my focal lengths and my radius of curvature. Let's look at the first line. So, line 1, parallel from the top of the object to the lens. Okay, if that's easy, let's draw that bit in. but then it goes through a focal point. But we saw in the picture a couple of slides ago that diverging lenses, concave lenses, they don't go through this focal point. They go away from this focal point. And so that's how I've set up this second line. I have to do this with a little bit more annoyance, but when you're doing this with a ruler, just line it up with your focal point to the top, or to the where your parallel lines come in, and then go out from there. Okay, so we can see there that this line is lined up with the close focal point. Line 2, straight through the middle. Okay, that one doesn't change. Line 2, always nice and easy. Line 3, okay, line 3 goes through a focal point to the lens and then parallel. Now, it's not going to go through this focal point, it's going to go through the distant focal point. So, line it up from the top to the distant focal point and draw until you get to the lens. And then, go parallel. And you can realize here, they're all diverging from each other, which, it's a diverging lens. It's what we would expect. But it's not creating an image somewhere. So we have to backtrace all our lines. So this one here, we're going to backtrace back down towards our focal point. This one here, we're going to backtrace back from our, this second line here, we don't need to do anything with that one because we can see here that it's actually crossed our second line. And our third line, we're going to backtrace back from the parallel point. We find that it's created the image right there. Again, it's a virtual image, it's on the same side. It is upright, but in this case, it is shrunk. Okay, so there's some slight difference there. Reduced is often a different word. Though smaller is perfectly fine. That's a big important difference between concave and convex. Now, it doesn't matter where you put your object, it'll always make an image there that is going to be virtual and upright. I don't recall if it's always smaller, quite possibly is, but it's worthwhile having a look at the simulation that's on eLearn. Okay. So when we describe that, I used a bit of language there. This is the syllabus says you've got to be able to do two following things. You have to be able to find the following for an object, or for an image of an object. You need to be able to find its location, which we just saw how to do, its orientation, and I used some of that language, but we saw that comes from the ray diagrams, and the size. Again, it comes from the ray diagrams. Through a single convex or concave lens. So there's only ever going to be one of those. It can't be both. Now, I did use the language, but here's our summary. An image pointing the same way as an object is said to be upright, and that means it's got a positive magnification. Okay. An image upside down is said to be inverted and will have a negative magnification. Okay. Now, that doesn't tell you whether or not it's bigger or smaller. Positive and negative just tells you, is it on the same side or is it upside down? Okay, but upright versus inverted is an important word to keep in mind. Now, if the distance to the image is on the same side as the object, okay, we call that a virtual. So same side, virtual. Any image created on the far side of a lens is called real. Now, thankfully, mirrors are the opposite, but we don't have to deal with mirrors, so that's good. Sorry, I'm just trying to find it. Now, to find the size is pretty straightforward. The height of the image is just found by measuring it. Okay. Now, the ratio of the image height to the object height is called magnification. That's what magnification is. How much did you make something bigger or make something smaller than? When you think about microscopes you did back in grade 8, or if you've done it in biology, you had a magnification of 400 times. It took the object and it made the image 400 times bigger. Now, anything bigger than 1 means the image is bigger. Anything smaller than 1, so like 0.5, means the image is smaller, like we saw with our concave lens. Okay, so these words, it's always a pair, one of these of the pair. So every image you would have to describe it's a virtual image or it's a real image. It's upright or it's inverted. It's bigger or it's smaller. You might have to measure the actual size, but again, as long as you draw accurately to scale, then you can measure the size. There would be a fair amount of fuzziness in those measurements, so don't get, like, if the exact answer is meant to be 1.5 and you get 1.4, that should be well within scope. Okay, so don't super stress about it. Now, there is a simulation on eLearn when you load up. It looks like this. It is very well worthwhile observing how the image changes as you move the object, the little candle over there on the left, from outside of 2F to in between 2F to F, and then in front of F. 2F in this case, remember, is just the radius of curvature. You can resize a lot of these things as well. Just note, the Ray 2 and Ray 3 is opposite from what I gave you. So their Ray 1 is the same one, Ray 2 is the bottom one, the opposite, and Ray 3 is the one through the middle. But yes, please have a play with that, just to learn just the general patterns, because as we said, there are only 3 examples, and so if you understand the patterns, then it makes it a bit easier for yourself. Now, this last section on equations, it is outside the scope of the syllabus. Feel free to skip it with no issue. I'm just providing this as a way of checking your work, because the math is not hard. I don't understand why this was not included. So there's a formula that describes the relationship between object distance, image distance, and focal length. It's called the lens formula. Okay, it's pretty straightforward. Just adding the inverses equals the inverse of the focal length. You'll note I haven't written any units on this because the units just have to be the same, like I said at the start. They can all be in meters, they can all be in centimeters, they can all be in feet, inches, rods, whatever. Okay, just make sure that they're all the same. There are a couple of important points when using the formula though. If your lens is a concave, then the focal length has to be negative. Okay, so if it says concave with a radius of curvature of 5, then f would be equal to negative 2.5. Okay? If your image distance ends up being negative, that means the image is virtual and to the left of the lens. Okay, assuming that your object's to the left. That's why I said I always put my object on the left. And so if di comes out being negative, then your image is also virtual. Pretty straightforward. There's also a magnification equation. Okay, so this is what we just saw before. That was the definition, but that doesn't help with making a prediction because you have to draw it and actually measure it. The second half of this equation is just this. Is the magnification is equal to the negative, okay, of the ratio of the distance to the image over the distance to the object. This one's a little bit trickier to remember. There's not like much that clues you into it. One thing I've noticed thinking, well, the definition for magnification is height of the image over height of the object, and still di over do. Just got to remember to slap a negative in it. The negative part isn't super critical to remember because you're going to figure out if it's negative or positive pretty quickly when you do your drawings. This is pretty good to think, well, did I have the right size? But, you know, it's up to you. Okay? You can't use these, though, to work out image characteristics. The syllabus expressly says you must use a ray diagram and that students don't need to know these formulas. So they mentioned saying, no, you don't need to know these. But they could be useful as a check. They can't mark you down if you use them and then you draw your ray diagrams. That's not a problem. Just got to make sure your ray diagrams are drawn properly. But that being said, this would be one possible question all across your exam, so please do not obsess over trying to do this. Get this correct 100% with all these extra little hidden steps. So, in a summary, okay, in the video we've done the following. We've described our features of lenses. We've learnt our 3 rules to draw our ray diagrams for lenses. We've learnt how to cheat ray diagrams using the lens equation. For your entrance slip to class, please complete questions 1 to 6 in chapter 16.7 Check Your Learning PDF and copy your answers into the 4.2.5 space on eLearn. Thanks very much for listening, guys. Have a great evening.